Okay, so in the last lecture, we define eigenvalue, eigenvectors, and then before that, we also saw the motivation to define that. So, what was our question in the last lecture? So, we had asked that can we find a basis for a vector space such that with respect to which the matrix of a linear transformation or linear operator is as simple as possible. This was the question. Or in terms of matrices, the question was, can we say that a matrix is similar to a matrix which is as simple as possible? And here simple means the matrix has many zeros, okay, as many zeros as possible. This was the question we had asked, and in order to do that, we saw that if we have like if suppose the vector space has dimension n, and if there are n one-dimensional subspaces which are invariant under the linear transformation, and also like their direct sum is equal to the whole space, then it is possible to find a basis. And with respect to this basis, the matrix of P is a diagonal matrix. So in particular, these one-dimensional invariant subspaces, they are of particular use or particular interest, and using them we define eigenvalue eigenvectors first for linear operators, and then we also parallelly define for eigenvalues for matrices. Okay. So now we have eigenvalues for an operator, and when we find a find a matrix of this operator with respect to some basis, then we have eigenvalues for that matrix also. So the next question is, what is the relation between the eigenvalue eigenvectors of a matrix of a linear operator and its matrix representation with respect to some basis? Or does it depend on the basis? So these are the questions we can just next ask, and we will answer in this lecture. Okay, so let me first state this result. In fact, we will prove that if we have a linear operator, then whatever basis we choose, the eigenvalues of this linear operator and the eigenvalues of its matrix representation are same. In fact, it is free of choice of basis. So no matter what basis you are choosing, the eigenvalues remain same for operator as well as for matrices. So the set of eigenvalues is exactly same for the operator and its matrix representation. So let us start the today's lecture with this result. So it says that, let me write the result first. Suppose that we have a vector space, let's say V, of finite dimensions. So assume that the dimension of V is n, and let us fix a basis, okay, any basis. So because if we want to talk about a matrix representation of an operator, then we need to fix a basis. So let B containing these vectors v1 to vn, this be a basis, okay. This is the basis of B. And suppose that we have a linear operator T on, then you can show that eigenvalues, so set of eigenvalues, this is the notation we are using for set of eigenvalues of T. So eig of T, that means the set of eigenvalues of T is equal to set of eigenvalues of matrix of T with respect to this basis. Okay, so now once we prove this, then you can see that this is true for any basis. So whatever basis you choose, this is true, and therefore it doesn't depend on the choice of the basis. Okay, and then this also gives us a motivation that since it doesn't depend on the basis, so choose a basis such that the matrix here is as simple as possible, so that we can easily calculate the eigenvalues. Okay, so let us prove this. This is very easy. The proof is not difficult. We just have to write it properly. So let us prove this. So this we have to show that these two sets are equal. Okay, so what I will do, I will start by taking an eigenvalue in of t, and I'll show that this is also an eigenvalue of matrix of t, and then the other side. Okay, so suppose that lambda is an eigenvalue of t. Okay, so let lambda be an eigenvalue of t. If lambda is an eigenvalue, then what we know? Then we know that there exists v which is not equal to 0 in the vector space v, such that t of v is equal to lambda v, right? You can write it this way also, t of v is equal to lambda v. But then what is this? Can we say something from this so that we can talk about eigenvalues of matrix of t? So see, what is our aim here? Our aim is to make this lambda as an eigenvalue of this. If you want to prove this, okay. So we want to say that lambda is also an eigenvalue of matrix of t. So what can we do from here?
This both
So
both are
this,
vectors.
yes,
uh, hence we मतलब हम इनको b के रिस्पेक्ट में लिख सकते हैं.
right, right. So if I take the, let's say, if I take the matrix representation of these vectors, then what it would be? It would be matrix of T, matrix of V, and lambda times matrix of V. Right. But then can we say from here that lambda is an eigenvalue of matrix of T? So can we say from here that lambda is an eigenvalue of matrix of T?
Yes, sir.
This we can say provided this vector is not 0 here. But why this is not 0?
We have taken v is not equal to 0.
Yeah, v is not equal to 0, and this vector contains the coordinates of v when you write v as a basis in terms of basis elements of v. So at least one of them would be non-zero because v is non-zero, and therefore this vector is not 0. So you can say that since v is not equal to 0 implies this vector here. This is also a vector. You remember, if you if v is in v, then if you look at this would be in Fn, right? If you recall, it is just the matrix of T. It's a column vector, so it would be in Fn. So this is not 0, but then this implies that lambda, by definition, lambda belongs to eigen of matrix of T. So the one side containment is fine. How about the other side? So conversely, let now suppose that lambda is an eigenvalue of matrix of T. Okay. Again, same, since lambda is an eigenvalue, so what does it mean? It means that it's a matrix of T, and matrix would be of size n cross n, right? Where the entries of this matrix are coming from the field. So what you can say from here, that there exists, same way there exists x not equal to 0 again in Fn, such that this expression holds times x, right? Now what we have to do, we have to use this information, and using this we have to make lambda as an eigenvalue of t. That means we need to produce a vector v in the vector space capital V such that t of v is equal to lambda times v. That is what we need to do. Now how can we do that? How can we do that? Any idea? So we need to produce a vector v such that T of V is equal to lambda times V. And this is the information we have here. Can you at least suggest some vector V using this that could possibly uh, a candidate for this?
Sir, X itself is a vector of V since X can
No,
be
X
written.
is not a no. X is not a vector of V. X is in Fn. F is the field.
So,
Sir,
Yeah.
x1 v1 v1 plus x2 v.
Yeah, I understand what you're saying. So she's saying that since X is in Fn, so assume that so suppose that since X is in Fn, so let's say X is of this form x1, let's say x1, x2, and so on up to xn. So it will have n coordinate. So using this, you construct this V, which is of this form xi, vi, I equal to 1 to n. This is V, this is n. Vi's are the basis vectors. Now this vector V, X itself is not in V, but if you consider this V, which is the linear combination of these, then this is a vector in capital V, that means in the vector space. And then you can verify or you can check whether this solves the purpose or not, or this is an eigenvector corresponding to eigenvalue lambda of t. That you can verify. Now, what you can say clearly from here that clearly since this x is not 0, so at least one of these xi is not 0 here, and therefore from here you can say that this vector is also not 0. Because if this vector v is 0, then this expression here, this linear combination is 0, but then this implies that all these xi's are 0 because these vi's form a basis. So this is not possible, right? So clearly this is not 0, right? Because as v1 to vn, they form a basis. So this is not 0. Now we just need to see whether T of V is equal to, so what is our claim now? Claim is to show that T of V is equal to lambda times V. If we prove that this is true, then we are done. So just check whether it is true or not. So let's say T of V is, so let me write here, T of V is I equal to 1 to n xi vi. But then t is linear, so what you can do, you can take t inside, so it would be xi t of vi, or let me write this j equal to 1 to n. So let's say j equal to 1 to n. Okay. So t of vj. Now what is next? See, we need to use the fact that this lambda is an eigenvalue of matrix of t. So from here, what we can say, t of vj. Now t of vj
lambda,
we can write, yes.
lambda, which,
Sorry.
lambda times Vj.
Lambda times Vj, we cannot say directly from here because Vj is not an eigenvector for t with respect to lambda. T of Vj, we cannot say lambda times Vj. How can we say that? I mean, we don't know whether Vj is an eigen. We can say that provided Vj is an eigenvector corresponding to eigenvalue lambda of t. But we are trying to prove that lambda is an eigenvalue, and we are trying to find an eigenvector for that. If you are saying that, that means you are already assuming that Vj is an eigenvector corresponding to eigenvalue lambda. We are trying to prove that. So we cannot directly write that T of Vj is equal to lambda Vj. So what else we can try here? We can do T of Vj. We have matrix of T. Can you use that? Because we have something for matrix. So here, so let us assume that this matrix of T, this has entries aij. Let's say. So what we can say from here, what it would be? J equal to 1 to n xj t of vj. Can I write this in this way? Using the matrix of t, I equal to 1 to n I equal to 1 to n aij vi. Is it okay? Because we have a matrix of t, so I'm using these entries and I can write t of vj in this way. But then now if you can change the summation here, you can interchange the summation and nothing would change. So the same thing I can write, I will take the summation with index I outside. So it would be, sorry, would be summation j equal to 1 to n aij xj bi. But now you can see what is this AI, the inside this in the summation with the index j. What is this? This you can tell me now. What is this? When you multiply this matrix of t with this x, what was this? It was lambda x. Now you can multiply this. This has entries aij, x has entries x1 to xn. What it would be? Would be summation I equal to 1 to n, summation j equal to 1 to n. Aij xj is simply lambda xi, not summation, without summation. So this summation inside this term here, this is equal to lambda times xi. So what we have is lambda xi vi. Lambda xi vi, I can take lambda outside, then it would be I equal to 1 to n xi vi. But then summation xi vi is just v, so it is equal to lambda times v. So this implies that P of v is equal to lambda times v. That means lambda belongs to I of t, and we are done. So the eigenvalues of t and eigenvalues of its matrix representation with respect to any basis, they are same. Okay. So what we can say from here, that eigenvalues of t do not depend on the choice of basis, whatever basis you take, and therefore it is important to find a basis such that the matrix of t is as easy, as simple as possible, so that we can easily compute the eigenvalues. So that's why we are trying to look for a basis such that the matrix of t is very simple, so that we can easily find. For example, if suppose we can find a basis, let's say uh, b of t. So this is a linear operator. So if suppose t is a linear operator and b is a basis, such that matrix of t is, let's say, diagonal, then I can easily tell what are the eigenvalues of t just by looking at the diagonal entries of this. They would be the eigenvalues of matrix of t, but then they are same as eigenvalues of t because of this result. If I'm not able to find a diagonal matrix, then maybe, let's say, can we find a basis such that the matrix of t is upper triangular, let's say. Then again, I can look at the diagonal entries and I can easily tell what are the eigenvalues. They are diagonal entries. So that we also find. So choice of basis is very important here. So we will see how whether we can always find such a basis such that the matrix of t is very is simple. We'll see that. But you can now at least feel the importance of finding the basis so that the matrix of t is as simple as possible. So what we can say from here, that the eigenvalues of t do not depend on the choice of basis, and this also gives us a way to define determinant of a linear operator. So I can write this as a, just for your records. that eigenvalues of t do not depend on the choice of basis. This is because of this result. Secondly, how to compute these eigenvalue eigenvectors? So there is a way, it's an easy process to compute this, computing eigenvalues and eigenvectors. I mean, in theory there is a way, and then in practice also one can do, but that is different. If suppose now you want, so you know how to compute eigenvalues of a matrix, right? So what you will do, you will look at the characteristic polynomial, and then the roots of the characteristic polynomial, they are the eigenvalues, so you will get the eigenvalues. Once you know the eigenvalues, you will look at the corresponding eigenspaces, and then from there you will get the corresponding eigenvectors, right? For every eigenvalue you will look at the eigenspace, find a basis for that eigenspace, you will get linearly independent eigenvectors. This is for matrix. How about the matrix of T? Because for matrix of T, so far what we know two things. If we want to, sorry, not for matrix of T, sorry, it's a operator. So how about finding eigenvalues of an operator? So far we know two processes to find eigenvalues of an operator. First is by definition. That means we need to find all such lambda and v for which this expression is true. Then we can say that t is v is eigenvector and lambda is the eigenvalue. This is by definition first, and the second thing is that instead of t you look at basis of matrix of t, and then you look at the eigenvalues of matrix of t, and then you find the eigenvalues. So that is another way because of this result, because the eigenvalues are same. Once you know the eigenvalues, then you can look at the eigenspace. This one, null space of this you know now. You can find for every lambda, you can find this eigenspace corresponding to that lambda. You find a basis for this, that will give you the corresponding eigenvector. So this way you can find eigenvalues and eigenvectors. In fact, you can also talk about characteristic polynomial of an operator. That means you can define determinant of an operator using the determinant of its matrix. So that's what I'm writing here, so that you know whenever we say determinant of an operator, what do we mean by that? Determinant of an operator means the determinant of its matrix representation with respect to any basis. It doesn't depend on the basis. So let me define this. So determinant of t. So we define determinant of t as determinant of, whenever I say determinant of t, that means determinant of t is same as determinant of matrix of t, where b is any basis. This way I am defining this. So first we need to check whether whatever I have defined, that is well defined thing or not. Should be well defined, right? It well defined means it cannot have two determinants. So I am saying here any basis. So you take two bases, any two bases, and then check their check the matrix of T with respect to these two bases, and look at the determinant. If both of them are giving the same determinant, then this is fine, because it doesn't depend on the basis. So this definition is fine. So we should always get a unique value for the determinant. So what I'm saying that it is, we have to check whether it is a well defined thing or not. So well definedness we need to check. Well definedness of this determinant. How to check that? You just take two, as I mentioned, you check two bases, any two bases. So let's say b and b dash. These are any two bases, and we should say that whenever I'm saying determinant of matrix of T, there are infinitely many bases, and there we can find the matrix representation of T with respect to these bases. But all these matrix representation giving you a unique value, and therefore you can say the determinant of T is the determinant of matrix of T with respect to any basis. It should be free of choice of basis. So if we take two bases b and b dash, then we should be able to say that determinant of t is equal to determinant of this, oh sorry, t with respect to b, or determinant of t with respect to b dash. It's the same thing. But why this is true? Can you tell me why these two determinants are same?
Determinant depends
Because
on
t beta
eigenvalues.
and t beta dash are similar.
Yes, it's not because determinant depends on the eigenvalue. We have not discussed that yet. So you are using something which we have not discussed. So what we have discussed in the class so far?
Because t beta and t beta dash are similar matrices.
They are similar matrices, right? This is true because matrix of T with respect to B and matrix of T with respect to B dash, they are similar. That means there exists an invertible matrix P such that this holds. And now you can take whenever you take the determinant of T with respect to B, it would be same as the determinant of T with respect to B dash using the determinant property that determinant of AB is equal to determinant of BA, or you can also use determinant of AB is equal to determinant of A times determinant of, right? So this way you can now talk about the characteristic polynomial. That means what you will do in order to find the eigenvalues, you first find the roots of the characteristic polynomial the same way as you have done for matrices. We want to develop parallel theory for operators as well as for matrices. So whatever you can say for matrices, similar thing you can say for operators also, and the other side is also true. That is what we are trying to develop here. So find the roots of the characteristic polynomial. Now you can talk about the characteristic polynomial. What is that? It is, you can denote it by this notation, p subscript t z. It is determinant of t minus zi or zi minus t. Let us be consistent with the notation, so we can write it zi minus t. This is the determinant. This is the characteristic polynomial. So now you can talk about determinant of zi minus t. This is an operator, so it is just a, you can also write it in this way, or you can find roots of the characteristic polynomial of PAZ, which is determinant of zi minus a zi minus a, where what is a? A is the matrix of T with respect to any basis. The same thing this you can do, and then the next is finding. So this will give you the eigenvalues, and the next step, find basis for E lambda. That means null space of P minus lambda I. Okay, for each lambda in the eigenvalues of the set of eigenvalues of T. So this step will give you the eigenvalues, and this step will give you the eigenvector corresponding to each eigenvalue lambda. Okay, so far what we know, we have defined the eigenvalue eigenvectors for operators as well as for matrices. We also know a relation between the between the eigenvalues of operator and its matrix representation, and we also know a way to find eigenvalue eigenvectors of an operator as well as of a matrix. This is what we know, but we have not discussed yet whether eigenvalue exists, whether a matrix or a linear operator always has an eigenvalue. So existence of an eigenvalue we have not discussed. We have discussed something from the definition, but we have not discussed whether a matrix or an operator always has an eigenvalue. So for example, so let us put up this question first. So the question we want to answer next is whether any given matrix, let's say A, or let's say T, linear operator T as an eigenvalue. So A, I am saying is the square matrix. So you understand what question I'm asking here. So whether any matrix, or similarly you can ask for operator, or any operator T as an eigenvalue. So what is your answer here?
No.
Not always.
No? So okay.
फील्ड पे डिपेंड करेगा
No, field पे depend करेगा, right? Okay, can you give me an example of an, let's say,
The
of a
Zero
rotation
one.
matrix?
operate. The rotation operator जो है cannot have
Yes.
eigenvalue.
Yeah. Yes, I understand. So you if you look at here, what you try to do here whenever you find eigenvalues, so um, eigenvalue by definition is something like this, right? So you can think about a rotation operator. That means, so what by definition of an eigenvalue, V a vector is an eigenvector if when you apply T on V, it remains either in the same direction or or it changes the direction. That's the only thing. But it doesn't rotate. So if V is a vector, when you apply, this is an eigenvector, when you apply T on this, then either it goes to this direction, somewhere it will scale in this direction or in this direction. That's all. But it cannot like change the angle. Okay. So now if you take an operator that every time changes the angle, so that means you can rotate a vector. So whenever you have V, you apply TV such that this is your T of V. So every time you change the vector by some angle, so let's say take some rotation with respect to any angle, that operator cannot have an eigenvalue in R2 here, right? This is the idea, and therefore at least in R2 you can say that it will not have an eigenvalue. So for example, I can explicitly write also. So let's write this example first for operators. So if you take let's say V as R2 and T is the rotation, you can take any rotation. So let me take this um, rotation in clockwise direction by 90 degrees. So it would be y minus x. This is for all xy in R2. Now this vector, this matrix, this operator doesn't have a real eigenvalue, and so it doesn't have a eigenvalue because here we are considering R2 over R, so it doesn't have any eigenvalue. So then this T has no eigenvalue. Why it doesn't have eigenvalue? That also you can prove. You can, as you mentioned that, as I mentioned the idea, but you can also prove it in like with the mathematical argument. You can also prove. So what you have to show that T has no eigenvalue. It means that whatever lambda you take, whatever real number lambda you take, you cannot find a vector in R2 such that T of V is equal to lambda times V. So that is what you have to prove. So you can say that why this is not true, because for any lambda, if you take in real and vector xy in R2, and if you want to have it as an eigenvalue, that means it should satisfy this kind of thing, lambda xy. So what is lambda x of x comma y? It is by definition y comma minus x. Now if you compare these sides here, left hand side and right hand side, you will get y equal to lambda x and x minus x equal to lambda y, right? But then this implies that 1 plus lambda square x equal to 0. Now lambda is the real number, so 1 plus lambda square cannot be 0. It is always positive. So this implies x is 0. But x is 0 and y is just lambda times x. So this implies y is also 0. So that means whenever such a condition, such a expression is true, this implies that x and y both are 0. So that means it's a 0 vector, so it cannot be an eigenvector, and this is true for any lambda. And therefore, implies that there does not exist a vector xy which is non-zero in R2. Of course, in R2 we are talking such that P of x comma y is equal to lambda times x comma y for any lambda in R, and therefore this linear operator doesn't have an eigenvalue. Equivalently, you can say same for matrices also. One of you were giving one example. So you can consider this matrix A, which is you can consider as a matrix of P with respect to the standard basis. It is 0, 1, minus 1, 0. So what is the basis? I have taken E1, E2. Yeah. So then this matrix A doesn't have any eigenvalue. So A has no eigenvalue. But here, as one of you mentioned also, if we change the field, that means if we consider same map over R2, so same operator over C2, sorry C2, then it will have an eigenvalue. So then you can check that it will have two eigenvalue plus I minus I. So plus minus iota it will have. So if we change the vector space as C2, and if we consider the same operator, then it will have an eigenvalue, but over R2 it will not have, or over R it will not have an eigenvalue, right? So not every linear operator or a matrix has an eigenvalue, but if the underlying field is the field of complex number, then you can prove that it will always has an eigenvalue. Okay, it will always have an eigenvalue, have at least one eigenvalue, and using that you can actually prove that it will have exactly n eigenvalues, where n is the dimension of the vector space. Or if you're talking about matrix, if the matrix is over the field of complex numbers, then n of size n cross n, then it will have exactly n eigenvalues. All right. So the next we will prove the existence for of an eigenvalue on a complex vector space or on a complex matrix. So let's say, so let me write this as a result first. So in general, this is not true as we have seen in the example, but if the field is the field of complex number, then it is true. So you can prove that, suppose that V is a finite, so let V be a finite dimensional vector space over C, then T, any operator or every operator on V has an eigenvalue. Is an eigenvalue that you can prove. So let me write this proof here. Okay. So let me before I prove this, let me recall that. Let me recall this here. So first recall, before I start the proof, let us recall this thing, that if suppose we have a operator T on V, where V is a vector space over F, and this is any polynomial over the set of polynomials over the same field F. Oh, sorry, element. Okay. So this is a polynomial, and so let's say Px is of the form a0 plus a1x and so on, an xn. Then If T is a linear operator, then you can check that this P of T, where you just replace X by T, then that is also a linear operator on V. So that means you can verify that, then this is again a linear operator. So this also belongs to the set of linear operators. So this is linear operator. And this is called polynomial in T. So this is called polynomial in T. This is the first thing I wanted to recall. The second thing is that is the fundamental theorem of algebra. What it says that every non-constant polynomial over C has every non-constant polynomial of degree n over C has exactly n roots, right? In fact, if you have a polynomial, let's say if this polynomial is over C, then you can actually write a factorization of this polynomial in linear factors. Right? So this is the fundamental theorem. I can write the here also fundamental theorem of algebra. I'll use both these facts here in the proof. So it says that every non-constant polynomial over C has a root. Okay, this is one statement. Equivalently, you can write different statements also. Okay, so let us using this we will prove this result that every operator on a finite dimension vector space over C has an eigenvalue. Okay, so it's a finite dimension, so assume that n be the dimension of. Okay, so we start the proof now. Suppose that n is the dimension of V, and take any vector. So any vector, it's any non-zero vector. So any, let's say any non-zero vector I have taken here in V. And using this, consider the set S, which is actually this one, V, TV, then T square V, and so on up to Tn of V. Now, what can you say about this set S? This is a subset of V, right? T is an operator on V, so this set is a subset of V. What can you say about this set? Is this set linearly independent or dependent? Can you say something about this?
We can't comment.
You can't comment. Look at this set again, and then see.
Sir, linearly independent.
Linearly independent.
Yes, sir.
Look at this set again. This is a subset of V. What is the dimension of F?
Sir, linearly dependent.
Why?
Sir, n+1 vectors.
Yeah. So there are n+1 vectors. The dimension of V is n. So it cannot be linearly independent. So this set is clearly linearly dependent. If this is linearly dependent, then by definition, you know that there exist scalars a0, a1 and up to, let's say, an in C, where not all of them are 0, not all 0, such that a0 V plus a1 T of V plus and so on up to an Tn of V is 0. Let us call this star. This equation as star. Okay, this is fine. This is because S is linearly dependent. Since this is 0 and one of them is not 0, this one of the scalar, at least one of the scalar is not 0. So I can take the m. So I can take, let's say, m with the largest integer such that am is not 0. Right? I know that they are not, all of them are not 0. So I will check. I'll take. So let m be the. This I can assume that, suppose m be the largest such that am is not 0, but the rest of am plus 1 and so on, they are 0. I'm choosing the largest one, which is not 0. And then consider this one. Now consider this polynomial now. Consider this polynomial pz, where I'm constructing this polynomial using the scalars a0 to am, the same scalar. So a0 plus a1z and so on up to amz. Okay. Now clearly this is a polynomial over C, where the degree of polynomial C, this polynomial P is m. M. So this is a polynomial over C. So it will have exactly m roots, and therefore we can say that there exists a factor. We can write this polynomial in this form: C z minus, let's say, lambda 1, z minus lambda 2, and so on up to z minus lambda m, where this C is a non-zero complex number, and this is true for all z. Okay. So this we can write because this P, we can construct this polynomial over this using these scalars a0 to am. This is a polynomial over C. So by fundamental theorem, we can write this pz in this way, because we know that it will have m roots. So we can get a factorization of this form where this constant C is not 0. But then it is same as we mentioned, it is P of t. When I look using this polynomial, if I find the polynomial in t, then it is C, then t minus lambda 1 I. In terms of polynomial, it would be this one, y, and so on up to t minus lambda m I. Right?
सर
Yes.
तो सी को डायरेक्टली एम नहीं लिख सकते?
C directly, you need to. So I'm not saying that this C has a particular value here. Because I don't know this what kind of polynomial it would be, what would be the CM, and what are these factors. What I know is that since this is a polynomial over C, it will have this kind of factorization because of fundamental theorem. I'm just using that. I don't care about what is this C is. I don't care what this C is. I just need this factorization. So I'm writing it in this way. Okay, so I don't know what is this polynomial exactly. What I know is that it is a polynomial of degree m of C, and therefore I can use the fundamental theorem of algebra. That is what I used, and I have written a factorization for this. That's all. We don't need anything from this C. We just need that this C is not 0. Is it okay? So you don't have to tell what is this C is, what this C is here.
ओके सर,
But
बट
then
डायरेक्ट एम तो आ रहा है ना सर, सी इक्वल जो आपने फॉर्म लिखी है, ठीक है, वो तो कि हमें सी की जरूरत नहीं है, बट यहाँ से एम आ रहा है ना.
okay, I don't see it here, but it's okay if you can see. I don't need this actually here. So if you can find this C, it's okay. But I don't see it from here that
So
what is
z
this
to the
C.
power m,
Yes,
coefficient
is
of
J
z
to
to
the
the
power
power
M.
m. Yes, sir.
Yes. So it would be m right here. Just multiply. But we don't need this, so you can write it this way also, or you write am. But what we need is that you can find polynomial in T. We can write it in this way. Now clearly from 1, this is also polynomial in T. It's the same thing, right? This is also P of T, but this is P of T of V, right? This is the same thing, but in this way. Because you can write it as A naught plus A1T, so on up to A and T and of V. It's the same thing. So it's P of T of V. But then we know that this is 0. So since P of T of V is 0 from 1 from star, so this implies that C T minus lambda 1 I on to T minus lambda m I V is 0, right? Is it okay? But then from here, can you say that what can you say from this expression? C is not 0, so you can say that okay, you remove this also. C is not 0, so this is 0. What can you say from here?
At least one operator is 0.
Yeah, so you can say from here that there exists. So because if suppose let's say if this is not 0, let's say this factor is not 0 with V. If this is 0, then V would be an eigenvector and lambda m would be eigenvalue if this is 0, right? So we are done. We are proving, we are trying to prove that T has an eigenvalue. If this is not 0, then call this vector as let's say W. And then look at the next factor T minus lambda m minus 1I. Check that whether that is 0 or not. If that is 0, you are done. If that is not 0, then move to other and so on. But since this expression is true, this is the whole expression is equal to 0. You can say that there exists. You can say there exists W and not equal to 0 in V. You don't know what exactly what this W is, but what you can say that there exists W non-zero in V such that T minus lambda J I of W equal to 0 for at least one J. For at least one J in this set. But then this implies that lambda J is an eigenvalue of T and you are done. Is there any doubt in the proof? Is it okay? The proof is?
सर एग्जैक्टली 1 होगा ना?
From here you can say not exactly one, but you can say at least one. That is what we are trying to prove here.
सर W के करस्पॉन्डिंग तो एक ही लैम्डा होना चाहिए ना?
So there would be there exists W. So there would be for at least one J for which this is not 0.
Yes.
So
Clear.
see what I'm
लैम्डा
saying is that there may not be such V, but there can be some other V. What you can say from here that there exists W in V, capital V. You understand what I'm saying? From here, what we can say that there exists one W. One W we can find from here, but this says that there exists at least one W. There exists a W such that this is true for at least one J. But then there may be other V, other vectors which are true for other J's. You understand what I'm
yes, clear.
saying?
Yes.
Yeah. Okay. So from here we can say that it will have at least one eigenvalue. But then using the facts, now you know that it's a linear operator over C. It has an eigenvalue. Now you can look at the characteristic polynomial of T. It would be a polynomial over C of degree n if V is of dimension n. Then since it's a polynomial of degree n over C, and every polynomial over C has exactly, every non-constant polynomial over C has exactly, like if the degree is n, then it has exactly n roots, and therefore you can say that an operator on a dimension n vector space has exactly n eigenvalue if the vector space is over C. Similarly, you can say that every matrix parallelly or equivalently, you can say for matrices also, if A is a matrix, square matrix over C, then it will have at least one eigenvalue. Or you can say, using the fact that the characteristic polynomial is of degree n over C, you can say that every matrix over C of size n cross n has exactly n eigenvalues. Okay, so this gives the existence of eigenvalues. So equivalently, you can say, let me write for matrices also. You don't have to prove this. We have already proved this for operators. So it's you can equivalently prove for this also. So every matrix A of size n cross n over C has an eigenvalue, right? Okay, so let me give you an exercise, and then I'll ask you in the next class the answer of this or a solution for this. So the exercise is the following. Let P be a projection on a linear finite dimension linear operator on a finite dimension vector space V, and V is over C. Okay, so V is over C. V is a vector space over C. So P is a linear operator on a vector space V over C such that P square equal to P. So P is a projection. Okay. Then find the eigenvalues of, okay. So you have to give a complete answer to this. What would be the eigenvalues of P? So you need to give a set of eigenvalues for this P. Okay. So you answer this question completely. Okay. And I'll ask you this in the next class.
So dimension of V.
Dimension of V is let's say n. It's a finite dimension vector space. Let's say what would be the?
Yes.
You don't have to bother about the dimension. Let's say it's of dimension n. So you have to tell what are the eigenvalues. What could be the eigenvalues of this? All right. You can also easily prove that using this. That let me write this as a simple exercise or simple problem here. So you can prove that if P is an operator on a finite dimension. So we are talking about finite dimension vector spaces, or we are talking about matrices, then it is automatically finite dimension. So we are talking eigenvalue eigenvectors of operators on a finite dimension vector space. There is this notion of eigenvalue eigenvectors for infinite for an operator on infinite dimension vector space also, but then it is not that straightforward. So it is more complicated. So we are restricting ourselves to the finite dimension case. There you need some other things also in order to define that. So we are restricting ourselves to finite dimension, to operators on finite dimension vector space. So let T is a linear operator. Then you can they can say that T is invertible. This is very easy to check. You can verify yourself. T is invertible if and only if 0 is not an eigenvalue of T. Okay. This you can, this is if and only, so you can easily verify this. So this also you can verify. I'm not doing this. Just use the fact that just use the definition. That's all. So next result I'm proving is the following, that if we have a linear operator T, then the eigenvectors of T corresponding to distinct eigenvalues, they are linearly independent. So eigenvectors corresponding to distinct eigenvalues are linearly independent. So next is the following result. So let us suppose T is a linear operator on V. Then eigenvectors corresponding to distinct eigenvalues are linearly independent. This is what we need to prove. Okay. Okay. So you tell me how to start the proof. How to start the proof? We have to show that eigenvectors corresponding to distinct eigenvalues are linearly independent. Just tell me the start.
We'll take two eigenvectors.
Suppose v1, v2 dot dot vn is a eigenvector corresponding to lambda1, lambda2 dot dot lambda n.
Where?
Then we set a linear
So
combination.
what are just a minute. But then what are you are assuming that these are the eigenvectors corresponding to distinct eigenvalues?
So suppose v1 to vn.
Vn, okay.
Then
They
we
are the
take linear combination
So
a1 v1 plus.
just a minute. You are saying that take v1 to vn eigenvectors corresponding to eigenvalues lambda 1 to lambda n. I am saying whether these lambda i's are distinct or not. So you are assuming that these are vectors corresponding to distinct eigenvalues. So we have to prove that eigenvectors corresponding to distinct eigenvalues are linearly independent. So
Take two different eigenvalues.
So may I?
yes.
And
So that lambda1, lambda2 dot dot lambda k are distinct eigenvalues where k is strictly less than equal to n.
Yes, strictly less than equal to, then you are saying strictly and then
So
also
it is
saying equal to. It's
So,
less than equal to.
so corresponding
Okay.
to that, v1,
Okay.
v2 dot dot vk are eigenvectors.
Okay.
So now let us take the expression summation ai vi equal to 0.
So you are assuming that they are linearly dependent.
No,
So you are
no,
proving by contradiction or by definition of linearly
by
independent.
definition of how to check the linear independence.
Okay. So you are saying assume that a1 vi. So the summation. So let me write. Okay, what you are saying. v1 to vk is less than equal to m. Lambda 1 to lambda k, these are the corresponding eigenvalues, and then you are saying take this a guy, so a1 and so on up to ak vk 0, right?
Yes, sir.
Then
Now operate t both
Then?
sides.
operate t both side, ठीक है, then it will be a1 lambda 1 v1 and so on up to ak lambda n vn equal to 0 or vk equal to 0, right? Then
Uh, and
yeah, so your idea is like very close to the exact one. It's there's only one thing which you are missing. So you are trying to use the fact that these are distinct and that way, but you need to first ensure that these VIs. So if you want to conclude something from these, you have to make sure that whatever the VIs you have written in the combination, they are independent. Then only you can conclude anything from here. So anybody else? There was a girl who was saying something. I did not hear. So can you please repeat your argument? So there was a girl who was saying something, but her voice was very low. Okay. Anyway, so let me tell you what is this.
Sir,
So
may
yes, yes.
I? Sir, let us suppose two eigenvalue, then corresponding eigenvectors v1 and v2.
Hmm.
We prove it by contradiction.
Okay.
Uh,
So let's say
if
you are
v1,
saying v1, v2, lambda 1, lambda 2. Then
yes, sir. Suppose v1 and v2 are v1 and v2 are linearly dependent. Then
linear
v1 is
dependent. Okay.
scalar multiplication of v2, or v2
Okay.
is scalar. Okay. Then
Then
apply t both sides.
okay. Then it is lambda 1 v1 equal to alpha lambda 2 v2.
Then lambda 1 equals to alpha lambda 2.
Why? From here you have this one.
Then
From here you can say lambda 1 v1 minus lambda alpha lambda 2 v2 equal to 0.
then
Then
I can conclude. Just a minute, sir.
yeah, you can try that. You can try using that way also. Just see what is the problem you are facing. So I have only limited time, so I have to do it. So suppose that, as you mentioned, assume that v1 to vk. So let me write this. So let's say v1 to vk, these are the eigenvectors of t corresponding to, let's say, lambda 1 up to lambda k. So these are the corresponding distinct eigenvalues. Okay. So for example, for lambda 1, v1 is the eigenvector, and similarly for lambda k, vk. So this is what I mean. So v1 to vk, these are the eigenvectors corresponding to eigenvalue lambda 1 to lambda k, where the lambda i's are distinct. That means lambda I not equal to lambda j if I not equal to j. So they are distinct. Now suppose that these vi's are linearly dependent. Linearly dependent, yes. Suppose that this set is linearly dependent. If this set is linearly dependent, then we know that at least one of them can be written as a linear combination of previous vectors, right? So these are eigenvectors, so these are non-zero vectors. So you start from v1, let's say. You see v1 is, if you just look at v1, it is linearly independent, only one vector. Then you look at v2, whether v2 can be written as a linear combination of v1 or not. If yes, then if it cannot be, then you move to v3. If yes, then you say v2 can be written as a linear combination of v1. So what I'm saying is that since it's a linearly dependent, you can find and there would be at least one vi that can be written as a linear combination of preceding vectors. We have proved this, okay, in our lectures, and it is easy to see. So what I'm saying, you choose the smallest integer vm such that the first vector that can be written as a linear combination of previous one. So for example, v1 cannot be, then v2 you look at whether v2 can be written as a linear combination of v1. If yes, then you choose v2. If not, then you go to v3 and check the same thing. So what I'm saying is that let m be the smallest integer such that Vm can be written as a linear combination of previous one. That means Vm is in the span of V1 to Vm minus 1. Okay. Now what does it mean? It means that these Vi's V1 to Vm minus 1, they are linearly independent. because I am choosing m be the smallest. So no other element in this can be written as a linear combination of the other one. So these vectors are linearly independent, but Vm is in the span of this. Now, since Vm is in the span of this, what we can say that Vm. So this implies, since Vm in the span of this, so we can write that we can say that there exists a1 to am minus 1 scalars such that Vm can be written as a linear combination of this with these scalars. So that means a1 v1 so on to am minus 1 vm minus 1. Let us call this expression as a star. Now, as you were saying, apply t on star from left. Then what we get? Then we get left hand side would be lambda m vm, and the right hand side would be a1 lambda 1 v1 and so on up to am minus 1 lambda m minus 1 vm minus 1, right? So let us call this double star. Now what we can do in star I can multiply this equation star from multiply this equation with lambda m from left hand side. So I can multiply star with lambda m, and then what I can do and subtract from double star and subtract from double star. So what I get in the left hand side, it would be 0, the right hand side would be a1 lambda m minus lambda 1 v1 so on up to a m minus 1 lambda m minus 1 minus lambda m minus lambda m minus 1 vm minus 1, right? This is 0. So what does it mean? Since v1 to vm minus 1, they are all 0. v1 to vm not v1 to vm minus 1, they are linearly independent. So this implies since v1 to vm minus 1, this set is linearly independent, and so this implies that ai lambda m minus lambda I equal to 0 for all I equal to 1 to m minus 1, right? Because they are v1 to vm minus 1, they are linearly independent, so that means this scalar should be 0 for all these scalars. So that means ai lambda m minus lambda I equal to 0 for all I from 1 to m minus 1. But then since we know from here, since we know that ai lambda i's are distinct, this implies that ai's are 0 for all I equal to 1 to m minus 1. But then if all ai's are 0, then what does it, do we get any contradiction? If all ai's are 0, then
Vm equals to 0.
VM 0.
yes. So from
So
here,
Vm
from
can't be
star,
0.
yeah, vm can't be 0. From star, we have we get vm equal to 0 because from star these are the combinations. So we get vm equal to 0, which is a contradiction because vm is an eigenvector and it cannot be 0. And therefore, whatever we have assumed here that these scalars are these vectors are linearly independent, that is not true. And therefore, eigenvectors corresponding to distinct eigenvalues are linearly independent. All right, so let's move on. Now we define geometric and algebraic multiplicity. So let me write this. Geometric and algebraic multiplicity. Multiplicity of an eigenvalue of lambda, whether it is eigenvalue of t or eigenvalue of a. A is a matrix, t is an operator. So I'm defining both the terms for I'm defining these terms for both matrices as well as for operators. Okay. So let us first define geometric multiplicity. Geometric multiplicity of an eigenvalue lambda. So what is that? It is the dimension of the eigenspace corresponding to this eigenvalue. Dimension of eigenspace E lambda. So what is E lambda? E lambda, if you're talking about operators, then is this null space of T minus lambda. And if you are talking about matrix, then it is the eigenvalue of null space of A minus lambda I. Okay. This is called the geometric multiplicity. So the dimension of the eigenspace this is called the geometric multiplicity. Geometric multiplicity. Let me write this. Geometric multiplicity G dot M dot of lambda. Similarly, we can define algebraic multiplicity of an eigenvalue lambda. So what is that? This is the multiplicity of lambda. Multiplicity of lambda as a zero of the characteristic polynomial. That means either PTZ or PAZ. PTZ, we are using the notation for characteristic polynomial of T, and this is for characteristic polynomial of a matrix. This is called the algebraic multiplicity A dot M dot of eigenvalue lambda. Okay. So what is geometric multiplicity? For each eigenvalue lambda, we can find the eigenspace, and whatever will be the dimension of the eigenspace, that would be the geometric multiplicity. So basically, geometric multiplicity is the number of linearly independent eigenvectors corresponding to an eigenvalue. What is algebraic multiplicity? Algebraic multiplicity is the multiplicity of lambda as a root of the characteristic polynomial. So we know that eigenvalues are nothing but the roots of the characteristic polynomial. So you just look at how many times it is appearing as a root of the characteristic polynomial. That would be the algebraic multiplicity of lambda. Now the question is, what is the relation between these two? So for example, we can just for understanding, we can construct easy example before proving a relationship between these two multiplicities. So you can look at this example. Let's say here, this is a diagonal matrix containing 1, 2, 3, 4. Can you tell me what is the algebraic multiplicity of? So what are the eigenvalues of this? Quickly, they are the diagonal entries. So what are the if lambda is an eigenvalue for this A, what is the geometric and algebraic multiplicity of that lambda?
1,
1 for each eigenvalue.
1 for each. So you can say that this is true, this is equal, and 1 for all lambda in the as an eigenvalue of T, in the eigenvalue of T. Let us take this one. This is again a diagonal matrix. What can you say about the algebraic and geometric multiplicity of 1?
Algebraic.
Sorry?
AM of 1 equal to 2.
And what is GM of 1?
Also 2.
equal to
So
1.
they are same. What about the other eigenvalues?
1, 1.
They are 1, equal to 1, 1. Okay. How about the Okay, so let me just write this also. So you can see in the first example that they can be same for all eigenvalues. In the second example, you can see that they are same. I mean, uh, for different eigenvalue, geometric and algebraic multiplicity can be different, but for a particular eigenvalue, they are same. But look at this example now. See, it is this one. So what are the eigenvalues of this matrix? What are the eigenvalues of this matrix?
1
Only one?
0
1 0 0.
100.
100. So the two distinct eigenvalues, 1 and 0. So what is the algebraic multiplicity of 1?
1.
1
And geometric multiplicity?
1.
1.
1
And what about 0?
Algebra
What is the
Algebraic
algebraic
2
geometric.
and geometric 1.
geometric 1? So algebraic multiplicity of 0 is 2, which is not equal to 1. 1 is the geometric multiplicity. So you can see here that geometric and algebraic multiplicity in these three examples. These are just simple example, but in general also you can prove a relation between geometric and algebraic multiplicity. In all these examples, you can at least say that algebraic multiplicity for an eigenvalue is always greater than equal to geometric multiplicity, right? So for in all these three examples, we can conclude different conclusion, but one thing is clear, which is algebraic multiplicity for an eigenvalue is always greater than equal to geometric multiplicity, and in fact one can prove it. One can prove this result. One can prove that if so. Let me prove this for matrices, but a similar result can be obtained for operators also. Okay, so let A be an n-cross n matrix and lambda be an eigenvalue of A, then algebraic multiplicity of lambda is always greater than equal to geometric multiplicity of lambda. This you can prove. So I have only 5-6 minutes. So the proof is not difficult. The proof you can also find in any standard textbook. Let me try to give you some idea. So what we have to prove here, we have to prove. Let me see how much I can do in this. The proof is not difficult. Proof is very easy. What we have to do, we have to show that the algebraic multiplicity is always greater than equal to geometric multiplicity. So assume that k be the geometric multiplicity of lambda. Okay? So k is the geometric multiplicity means what? K is the dimension of the, by definition, it is the dimension of the eigenspace. So that means eigenspace is null space of A minus lambda I. This is the dimension of eigenspace. This is the, now what we can do, since this null space of A minus lambda I, it is a subset of, it is a subspace of Cn. A is a n cross n matrix. So it's a subspace of Cn. So what I can take, I can take a like a basis for, so I can take a basis for this subspace. So let v1 to vk this be a basis of uh, this eigenspace. So eigenspace is E lambda. Okay, so it is this one. Okay. Now this is the basis. I can extend this basis to a basis of Cn. It's a this vector. This eigenspace is a subspace of Cn. This v1 to vk, they form a basis of the eigenspace. So I can extend this basis to a basis of Cn. So I can do that. So extend this basis to a basis of Cn. So it's V1 to Vk, and then add some vectors. Let's say Wk plus 1 to Wn. They form a basis for Cn. And then using these vectors, because they are elements in Cn, you can construct a matrix. Let us call this matrix as P, where the columns of these matrix are nothing but these vectors V1, V2, and so on up to Vk, and then Wk plus 1 to Wn. Okay, this is clearly an n cross n matrix because these Vi's and Wi's, they are of size n. Now when you multiply A with this P from right hand side, what do you get? So let us see. So this is A, and what is P? P is V1, V2 to Vk, and then Wk plus 1 to Wn. When you multiply this, you can check that this is same as multiplying this. The first vector is the first column vector is, or the first column of this product is AV1. The second would be AV2, and so on up to AVK. The next column would be AWK plus 1, and so on up to AWN. So first column is the product of A and V1. The second is A and V2, and so on. But since the first V1 to Vk, they form a basis for the eigenspace. Eigenspace means they are the eigenvectors corresponding to eigenvalue lambda. So you can write that the first k columns it would be lambda v1, the second one would be lambda v2, and so on up to lambda vk. These vectors you know that it would be this one, but then the other vectors you don't know, so you just write them as it is. Okay. Now this you can now verify that you can write this. So this vector here you can write as this lambda times v1. So see here, P is this matrix here. It's an n cross n matrix. If I multiply P from right hand side by EI, so if I do this P EI, that means I'm multiplying n cross n matrix P with the ith standard column vector. Then it would give me ith column of P. Ith column of P. I'll get the ith column of P. That means it would be whatever be the ith column, it would be that when I multiply P with EI from right hand side, right? So in particular, if I multiply P with E1, then it would give me V1 and so on. So basically lambda V1 I can write as this one. So lambda V1 I can write as lambda times P E1. Similarly, second one I can write as lambda times P E2, and so on, lambda times P EK. I can write it this way. Up to K, I can do this. And the next vectors, what I can do, I can write them as P inverse, because P is invertible here. All these VI's and WI's, they are linearly independent. So P is invertible. So I will write it in this way, AWK plus 1. And the next vector would be, the last vector would be P inverse AWN. So I'm just multiply P inverse, which is identity. So I can do that. Now I will take again, as I multiplied here, I can, it is the same thing as saying P and then lambda E1, lambda E2, and so on up to lambda EK. And then this would be P inverse AWK plus 1, and so on up to P inverse AWN. Right? So this implies that this I can write it in this way. If you look at the first K column, what it would be? It would be lambda, then the rest of the things are 0 in the first column, and the second, the two entries lambda. And so basically we will have this kind of factorization for this. This is 0, this is 0, this is 0. But then here it would be these columns. That I don't know what are these, so I will write them as just star. I don't care what are these. What I know is that the first one block would be a lambda times identity, and it would be of size k cross k. Okay. Now this is equal to AP. The left hand side is equal to AP, and P is invertible. So I can take I can multiply with inverse from left hand side. So what it would be? P inverse AP is equal to this lambda here 0 and this one. Right. Now look at the characteristic polynomial of A. What it would be? So if you look at the characteristic polynomial of A, it is determinant of z I minus A. But then you know that the characteristic polynomial of A and in any similar matrices are same. So characteristic polynomial of this is same as characteristic polynomial of this one, because similar matrices have the same characteristic polynomial. And then what it would be? What would be the what it would be? Determinant of zi minus what is P inverse AP? It is this matrix. And lambda is in the first k cross k block, and then this one. So what can we say from here? Can you tell me what it would be? So it would be z minus lambda I. Oh, sorry, lambda. What I can say, this polynomial would be, if you look at this determinant, it would be z minus lambda times k, uh, uh, appearing k times. So this factor would be appearing k times, and then there would be a polynomial. I don't know which one, but I can call this as gz, where degree of this polynomial gz is less than equal to n minus k. Right? So this would be the determinant. But then can you say from here that the algebraic multiplicity of lambda would be at least k from here?
Yes, sir.
Yes. So from here you can say that algebraic multiplicity of lambda is always greater than equal to k, because there would be at least k. There may be lambda may be appearing as a root of gz, but what you can say that algebraic multiplicity of lambda would be at least k, but k is the geometric multiplicity. So you can say that algebraic multiplicity is always greater than equal to geometric multiplicity. Okay, we can stop here, and today we will have a tutorial at 2 o'clock. Okay, we can stop now.
Thank you, sir. Have a good day.
Thank you, sir.
Same to you.